Hi guys, my name is IBM and today I decided to record 9702 52 February March series 2022. This is paper 5, planning, analysis and evaluation. So without wasting time, I'll take you to the question paper direct. So this is the question paper I'm trying to solve. And in my solution, I try to give you details and the format of how an SC to question number 1 and how we do analysis to question number 2. Therefore, these videos should be very useful to you. So without wasting time, let's go through the question paper. This is 970252 Feb March 2022. The paper is supposed to be 1 hour and 15 minutes, but because I'm writing on a computer, I have to draw on a computer, I may take more time. Okay, so I'll just go straight to the questions. Question number 1. A trolley with a magnet attached is placed on a thin steel sheet as shown in the figure. Okay, so when I look at the figure, first of all, I know that there is an angle here to be measured, so I will need a protractor. I will need a protractor to measure the angle theta. It's like I will need to measure distance d, so I will need a ruler here, a ruler to measure distance d. Of course, this trolley here, for safety precautions, I'll put a block this side so that when it reaches, I'll put a block here so that when it passes point X, it doesn't really cause any damage or any harm. Let me see what, of course, I will have to change theta, so that means you can use blocks, you can be piling blocks, but if you have experience, you know that I can use a jerk or a ratchet, an adjustable ratchet. So here to change theta, I may use a ratchet. So in my mind, I know I will put a ratchet here. Let this be the jaws for adjusting the ratchet. Or you could choose to use a jerk, a car jerk. So I have a ratchet, or you can use a jerk. So here, just move this piece here into these jaws so that I adjust the angle theta. Okay, so the angle between the sheet and the bench is theta. The distance from X to the trolley is D. So I'll measure D using a ruler. I'm now coming up with a sketch, a sketch of what I'm going to write in the essay. The trolley is released from rest, which means the initial velocity is 0 and travels down the slope. The velocity v of the trolley at x is determined using a light gauge. So here there is no option for measuring time. I'm going to use a light gauge. Since I'm using only one light gauge, the best thing I will do would be I will attach a card onto this trolley. So this is going to be a card. And of course, as soon as the card reaches the position of the light gauge, the timer starts, and as soon as the whole card passes by, or the whole card has gone past X, the timer should be able to stop. So I need to put a light gate here, so I will have to clamp the light gate. So here I know I will have to clamp the light gate. This is just a skeleton of what I'm going to write. So I have to clamp a light gate, and of course it must be connected to a timer. So I will need a timer somewhere. So this is a clamp this is a stand which has, of course, a clamp which is going to hold the light gate. So I'll need the bench, the timer, the protractor. I'll need a block. This is going to be for safety, so that when the trolley passes point X, it doesn't cause any harm the other side. Okay. I think that is all I would need for this experiment. So I just need now to go to the next part. It is suggested that V and theta, V is related to theta by the ratio. So it's like V and theta are the ones being investigated. So all I need is to notice which one is going to be dependent and which one is going to be independent. Remember, dependent changes when the independent has been changed, and the independent is changed by the experimenter. So it is easier for me to change theta as the experimenter. So my independent variable is going to be theta. And when I change theta, it means V changes. So the dependent variable is going to be V, which is the speed at X. Okay. They have given us a relationship. Since we are investigating theta, which is the independent, against V, which is the dependent. Remember, when I was sketching a graph, when we sketch a graph, we always sketch a graph with the independent variable on the x-axis and the dependent variable on the y-axis. So what I'm going to do is I'm going to make anything related to V, anything related to the dependent variable to be the subject in this equation here. So it means I'm going to take 2d to the left-hand side. So I'll have 2d times mp sine of theta minus qb times 2d should be equal to mv squared. So when I make v squared the subject, I don't need to find the square root, so I'll simply say v squared is going to be 2d times p. Of course, I've divided by m, so this is going to be sine 2d p sine theta, 2d p sine theta. Then minus, I'm dividing by m, so it will be 2 d q b divided by m. So I have made v squared the subject because v is the dependent variable. So I make anything related to the dependent variable to be the subject so that it's easier for me to carry out this investigation. If I compare this with y equals to mx plus c, I know that if I plot on the y-axis, I plot v squared, and on the x-axis, I plot sine theta because theta is the independent variable. So if I put sine theta on the x-axis, then it means the gradient is going to be m is 2d p. That will be the gradient. So it means I can find p. Then the y-intercept is going to be negative 2d qb divided by m. So that will be the y-intercept. Okay. So they want us to plan an experiment to test the relationship between v and theta. We must draw a diagram. We must explain how the results could be used to determine the values of p and q. Since I have the gradient and the y-intercept, it means I have also an idea about p and q. In your plan, you should include the procedure, measurements, control variables. Those are the quantities we are going to keep constant. Analysis of data, I will plot a graph. Then I can talk about the graph to find p and q. Then any safety precautions, I said I would put a block here at the end of just beyond x so that, no, I'll put a block after x. I want it to be, let's say, I'll put it here. Because the trolley is relatively bigger, so I will put it somewhere after x so that in case the trolley has passed point x, it doesn't cause any further harm. So I'll put a block somewhere past point x. So I'll incorporate that in my diagram. Okay, let's now go to the real part. So I'm going to draw a diagram, but before that, I'll tell the examiner the independent variable and the dependent variable. So I can say in this experiment, theta is the independent variable. Theta is the independent variable, and V is the dependent variable. V is the dependent variable. So that is the first statement I have to make here. Then to collect, because I need to write the procedure, so to collect and analyze data, I will take the following steps. So these are the steps that I'm going to take. Number one, I'm going to measure the distance d using a meter ruler. Let me first sketch my diagram here. Let me forget to draw a beautiful diagram. So I'm going to draw, it's better you always draw a big diagram so that you give a good impression to the examiner. So this is the bench or the table, and I'm going to put here, if I take more time, you'll bear with me because I'm drawing on a computer. So this is going to be the metal sheet. And I'm going to support it with a jack or a ratchet. Some people call it a jack. I don't know how to pronounce that. Okay, you may want it to be very safe. You may decide to attach another block here, a very huge block. Just to secure the jack or the ratchet. So this is a jack. It is easy to adjust jack, or you can use an adjustable ratchet. This is actually ratchet, adjustable ratchet. So this is just a block. The purpose of this block is to secure the jack or the adjustable ratchet. Okay, I hope this is the spelling of ratchet. So I have to put X somewhere, but before doing that, let me draw the trolley. Okay, so that is the trolley. So I'm going to attach a card on the trolley. So the card covers all the way up to where the magnet is. So this is a card attached on the trolley, and I have a magnet here. Then I have a trolley here. Okay. Of course, I will need the length of this card because it is the card which is going to intercept the point. It is the card which is going to intercept the light gate. So I will need the length of the card. I will call it L. The length of the card, I will call it L. Okay. So I'll put the trolley there. Then I need to put a point X. Let me put point X here so that I don't cause congestion on my diagram. So I'll put X there. So I need to put a light gate. Of course, the light gate must be clamped. So I'll draw a light gate. Sorry about this. I'll draw a light gate here. So let that be the source of light. It must be connected to a timer. So I'll add a timer. So let me first draw the stand here. I'll put my stand far away because I will need a space for the block. It's always good to draw using a pencil so that you can draw a very neat diagram. Where possible, please make sure you use a ruler so that your diagram gives a good picture to the examiner. So that is going to be my clamp. So I am going to put my timer here. So that's going to act as the timer, and I'll put a block somewhere here just in case. I want to leave space for the protractor. So let me first do a protractor here. So you can draw a better diagram, but I'm just using this as a representation of a protractor. So this angle here is going to be theta, and I'm going to put a block just somewhere here. So that is going to be a block, just in case it is going to act as a stopping block, just in case the trolley passes point X. Okay, I think I've included almost everything. So I just need to label the remaining parts. Okay, so I'll use blue for labeling. So this is going to be the timer. This is going to be the light gate. This is a block, which is going to be a block to stop the trolley. And then this is a protractor. So we have a stand here. What else? What else? I think this is all I need for this experiment. I've tried to include everything that I need. So I think the rest I just need to put it in writing. Okay. So I'm going to follow the following steps. Let's say step number 1. Step number 1, I will measure D. Of course, this is a distance, so I will use a rule. And mark. And mark it on. So I want to mark it on the sheet so that D remains constant, because D is going to be a control value. So I'll measure D using a rule and mark it on the sheet. And mark it on the sheet to ensure that D remains constant throughout. So maybe people may want me to show them marking points as I do this. So the mere fact that I've been able to include a protractor here in the correct position, that means it qualifies to give me a mark. So there's a mark there. I've clamped the light gate, there's a mark. Have shown how I would adjust theta, so I have another mark there. I've put here stopping block, there could be another mark there, so those are almost 4 marks. Then identifying the dependent and independent variable, that is another mark. Then telling the examiner that I'll measure D using a ruler, which is correct, and then ensure that it remains constant. You have ensured that it remains constant by marking it on the sheet, and you have also been able to identify that D should remain constant. In almost you have 3 marks in 1 point. Of course, the examiner will look for only 15 marking points, and then he will give you all the marks. Even if you write more 20 marking points, there is no problem. So step number 2, I will measure M, where M was, what was M? I think M was the mass of the trolley, and M is the mass of the trolley and the magnet. So I will measure M. Of course, mass is measured using a balance. So I will measure M. I will measure M using a balance. And of course, there was also B, which was the magnetic flux density of the magnet. So I will measure and B. And B, of course, magnetic flux density or magnetic field intensity is measured using a Hall probe. And B, using, of course, it should be calibrated. A Hall probe must be first calibrated. So I'll measure B using a calibrated Hall probe. Okay. So if I know that I'll measure M using a balance and B using a calibrated Hall probe, that means I have another mark there. But remember, M and B should remain constant, because if they don't remain constant, they would affect the results. So, but if I do that, I'll write this. I'll write this third step about the Hall probe. Remember, your teacher must have told you that we're using the Hall probe. You must also always use it in both directions and then obtain the average value of B. So that is an additional point. So I'll say while using a Hall probe, I will measure B first in one direction. I'll measure B first in one direction, then in the opposite direction, then in the opposite direction, and obtain an average value of B. So if the examiner sees that you are able to know that B must be measured in two directions whenever you are using a Hall probe and then you obtain the average, then you have an additional point there. Okay, step number 4. Remember, B and M must remain constant. So I will ensure that M and B remain constant throughout. So the mass and the magnetic flux density should remain constant throughout. Because if they don't remain constant, then what is the spelling of throughout? It is throughout. Okay. So M and B should remain constant throughout so that they don't affect the results. Okay, then step number 5. Did I measure L, the length of the card which I've attached on the trolley? No, I will use a ruler. So I will measure the length L of the card which I've attached on the trolley. On the trolley, of course, measuring this must be using a ruler. Remember, the length L of the card is the one which is going to intercept the light gate, so that we record the time of interception. So if I know the length and the time of interception of the light gate, then I can find the speed with which the trolley reaches point X. So step 6, I will measure theta, of course, that is the angle. I will measure theta. Of course, to measure theta, I'm using a protractor. What is the spelling? So I'll measure theta using a protractor. as shown on the diagram. I've indicated this on the diagram. Okay, then step number 7. Of course, let me write step number 7. Okay, I can now release the trolley. I will then release the trolley and record the time it takes to pass point X from the timer. The time it takes to pass point So the timer is going to give me the time. So this is point X. The timer is going to give me the time the trolley takes to pass point X because I've attached the card onto the top of the trolley. Okay, so I will then release. I have so many errors in this essay. I'll then release the trolley and record the time it takes to pass point X on the timer. The next step is going to be now to determine the velocity. So how am I going to determine the velocity? Remember, it started from rest. Initial velocity is 0. And if we assume the acceleration is constant, then I think we shall find the velocity from just L over T. So I will determine, this is now step number 8. I will determine V, which was the velocity at X, from one equation which is L divided by T. Then step 9, I have of course to repeat a step. I will repeat step 6. I will repeat step 6. Do I need to repeat step 6? No. I will repeat step 7 and 8 for the same value of theta and obtain an average value of V. So I will repeat step. I will repeat steps 7 and 8 for the same value of theta and then I obtain an average value of V and obtain an average value of V. So I'll repeat step 7, where step 7 I release the trolley and record the time it takes to pass point X, and in step 8 I determine V from L divided by T, or from V equals to L over T. Okay, then step number 10. So I have now an average value of V. So step number 10, I'm now going to repeat step 6. That is now for a different value of theta. So I'll repeat step 6 to 9. I will repeat steps 6 to 9. This time it is going to be for different values of theta until until I have 6 sets of results. So until I have 6 sets of theta and 6 sets of v, then I'm good enough to go. So now it is time for analysis. Step number 11. Which graph will I plot? I've already seen which graph I will plot, so I'll just tell the examiner I will plot a graph of v squared. I think we said we are going to plot v squared on the y-axis and or against sine theta on the x-axis. Okay, so we now know the graph to plot. We are doing the analysis. We have seen that this graph should be a straight line but has a y-intercept. It doesn't go through the origin. So I will tell the examiner the relationship is valid if a straight line is produced which doesn't go through the origin. So the relationship is valid if a straight line is produced which does not pass through the origin. So the relationship is valid if a straight line is produced which does not pass through the origin. Okay, so what is the gradient? We mentioned that the gradient was, I think, 2dp. So the gradient was equal to twice dp. And they told us to explain how the results could be used to determine p and q. So since the gradient is equal to dp, so it means that p would be equal to gradient divided by 2d. Okay, that is for the gradient. We also saw that the y-intercept was equal to negative of 2b, was it 2bq? The y-intercept is negative 2dq over m. Two bqd over m, which means that if I wanted the q would be equal to negative m times the y-intercept divided by twice bd. Okay, I think I've already mentioned the safety precaution, but I can still add it here for safety because I've already added it on the diagram. So for safety, I will place a block below point X to stop the trolley. So I'll place a block below point X to stop the trolley. So I'm very certain what I've written here is enough to give me at least 15 marks. For example, I already have a clamped light gate, that is 1 mark. I have a block here, those are 2, 3, 4. Here they may not give me any more mark again, those are 4, 5, 6, 7, 8, Measuring M using a balance and using a calibrated hollow probe, those are 7. Those are 9. Improving the value of B while using a hollow probe, those are already 10. I will ensure that M and B remain constant. That is correct because they affect the results. Then I'll measure the length L of the card attached on the trolley. That is also correct. I'll measure theta using a protractor. This one has already been credited on the diagram. It will not be credited here. I will then release the trolley and record the timer, the time it takes to pass point X on the timer. Okay, that is fine. It's already credited. I will determine V from V is equal to L over T. That will give you a mark. Then this part of repeating step 7 and 8 for the same value of theta to get an average value of V, that would give you a mark. Then repeating step 6 to 9, that will not give you a mark. I will plot a graph, V squared against sine theta, that will give you a mark. Then analysis, the relationship is valid if a straight line is produced which does not pass through the origin, that gives you a mark. So I already have more than 15 marks. Then this part here, the gradient is equal to that. This gives you a mark, this gives you a mark. For safety, I've already created that. So you have so many marking points. Most of them are awarded as additional points. So you should now be able to write a very good essay for this question. Okay, I tried my level best to save time. Let's go to question number 2. A student investigates a circuit containing a capacitor and a resistor as shown in the figure. So we have a capacitor, resistor, they're in series. So a dual beam oscilloscope is connected across the capacitor of capacitance C and resistor of resistance R. The oscilloscope displays two traces as shown in the figure. The student determines the phase difference theta between two traces. It is suggested that theta and R are rated by this equation here. So all we need is to know which graph is being plotted first. The graph is plotted of tan theta against 1 over r. So I must ensure that tan theta is constant, is the subject, and indeed it is a subject. So I'll just break this down. So tan theta is equal to 1 over 2 pi fc times 1 over r. Let me change this to blue. So if I compare this with the equation y equals to mx plus c, you see that the gradient is 1 over 2 pi fc. So the gradient is going to be 1 over 2 pi fc. Values of r and theta are given in the table. Each value of r has a percentage uncertainty of plus or minus 5%. Okay. R values are given. They are given to two significant figures. So if I want to record 1 over r, the best thing would be to record two significant figures or more. Either I maintain the number of significant figures or I increase the number of significant figures. The advantage of not increasing but simply maintaining is that plotting is relatively easier. So I'll just maintain the number of significant figures, which is 2. Then we have theta and we need tan theta. Calculate and record 1 over r and tan theta. We are going to include uncertainties in 1 over r. So let me first record r. I'll first record r. Okay, so I'll first record 1 over r. I think I can even record 1 over r to more than two significant figures. That is even easier. Okay, because of the scale that I have here. So it is possible for me to plot 20.1, 0.2, 0.3. So I'll just add one significant figure. So the first one, 1 divided by 12. That is 0.08. When I divide this by 1000, no, I'm supposed to multiply 1 divided by 12 times 1 exponent 3. So it is 83.3. So this is 83.3 times 10 to the power of minus 3. So this is 83.3 times 10 to the power of minus 3. Then 1 divided by 16. So this is going to be 62.5 times 10 to the power of minus 3. Then I have 1 divided by 22. So this is going to be 45.5 times 10 to the power of minus 3. 1 divided by 33. So this is 030303. So it is going to be 30.3. Then I have 1 divided by 39. Which is 0.25, so it becomes 25.6 times 10 to the power of minus 3. 1 divided by 43. So this is 23.3. Make sure you use a calculator that is easy for you to use, so that you don't make any mistakes. Then on the vertical we have, normally we prefer to record normally if you have angles and you find tan, log, you normally prefer to ensure that the number of significant figures of the angle or the number becomes the number of decimal places when you find the ratio, when you find the tan, when you find the sine, when you find the cosine, when you find the log, it becomes the number of decimal places, or you can increase. So I have 80.8. So if I try to find tan 80.8, so this is going to be 6.174, or you can write 6.17. I think that's not going to be penalized. 6.174. Then tan, if you are always not sure about how many number of decimal places, you can always increase. 7.5. So this is going to be 4.511. Then tan of 73. So this is 3.271. Make sure you also round off correctly. Then I have tan of 65.2, 2.164. I have tan of 61.7, 1.857. And last I have tan of 59.3, 1.684. Okay, now let me look at, so you can always maintain the number of significant figures, or you can increase, but it is dangerous for you to reduce the number of significant figures. But normally I said, if we are finding ratios, we always prefer to change the number of significant figures to be the number of decimal places. So I have to add uncertainties here, plus or minus for 1 over r. So for those who don't recall, I want to remind, if you have a quantity y is equal to 1 over x over r, what is the uncertainty in 1 over r? So let me just show you this. That if I want the absolute uncertainty in 1 over r, this one is the same as r power 0 divided by r. So it will be a fraction in y over y is going to be 0, fraction in r over r plus. In the denominator you have r power 1, so it is 1, fraction in r over r, where this one becomes 0. So it's like the absolute in y over y is equal to the absolute in r over r. In other words, the percentage uncertainty in r is the same as the percentage uncertainty in 1 over r, to be precise. So if I want the absolute, of course, the absolute in y is going to be the absolute in r over r, then I multiply this by y. So I have to change the percentage to absolute, then I multiply it by y. So if I want to change 5%, so the absolute in y for the first one, it is going to be 5%, which is going to be 5 over 100. Then I multiply it by y. Remember, y is 1 over r. So this is going to be 5 over 100. This one here is 5 over 100, that is the fraction. Then times y, where y is 1 over r. For this particular question, 1 over r is 83.3. So I have 5 divided by 100 times 83.3. Of course, the power of 10 is remaining the same. So that is going to be 4.2. I'll just write 4.2. So I'll repeat the same. I'll just be replacing r. So 0.05 times 62.5. So this is 3.1. 0.05 times 45.5. That is 2.3. Then we have 0.05 times 30.3. That's 1.5. Then we have 25.6 times 0.05, which is 1.3. We have 23.3 times 0.05, which is 1.2. Okay, so these are going to be the uncertainties. You could also write the absolute uncertainties to one significant figure because it becomes even easier to plot them. There is no problem with writing absolute uncertainties to one significant figure. So next we now plot the graph. Plot a graph of tan theta against 1 over r. Include error bars of 1 over r. Draw the line of best fit and the worst acceptable straight line on your graph. So let's plot the points, and you have to write them somewhere so that plotting is easy for me. Theta. Okay, so I can now plot them from a piece of paper. The first point is 83.3. So 1, 2, 3, that is 83.3 is approximately somewhere there. Because each box is 1, 83.3, I'll plot very close to 83. Then on the vertical, I have 6.174. So 6.174. So I have 6. The scale on the vertical is, let me check. The scale on the vertical is 0.5 divided by 10, that is 0.05. Every small box 0.05. So I'll add 2 boxes to get 6.1. So this is 6.1. It is 6.17. 6.15 is one box, so it is approximately here. So I'll put my point approximately here. That is 6.174 against 83.3. My next point is 62.5. So 62.5 is in the middle of the box, and it is against 4.511. So this is 62.5, 4.5 4.51 is, when I add 1, so 4.51 is approximately 4.5. So it is approximately here. I hope I'm using the scale correctly. Let me check. 4.511 minus 4.5 divided by the scale, which is 0.05. That's less than, it's less than a box, so I can't put it beyond this. So it is very close to 4.5, so I'll put it here. The next one is 45 against 3.271. 45. Did I plot that? 4.5. Okay, 45.5, 1, 2, 3, 4, 5. 45.5 is in the middle of the box against 3.27. 3.27. Let me check with my scale. 3.271 minus 3.0 divided by 0.05, which is the scale. So I'll add 5 on 3.0. So 1, 2, 3, 4, 5. That is approximate 3 point. So it's approximately here 3.271. Then the next one is 30.3. So we have 31. So 30.3 is approximately 30, very close to 30, but it's against 2.16. So I'll check the scale. 2.16 minus 2 divided by 0.05. I'll add 3 squares on 2. 1, 2, 3. So it's approximately here. Then the next one was 25.6. 1, 2, 3, 4, 5.6. I'll just take approximately 0.5. Then it was against 1.857. So I'll say 1.857 minus, what is the nearby? It is 1.5 minus 1.5. Then I divide by the scale. Let me repeat this. 1.857 minus 1.5 divided by the scale. Those are 7 squares. So we have 1, 2, 3, 4, 5, 6, 7. So it is around here. Then the last one is 23.3. So I'll just take 23, 1, 2, 3. 23 is approximately there. Against 1.685. Just try to check that. 1.684 minus 1.5 divided by the scale. So on the vertical, add approximately 3.5 boxes. So 23.3, 1, 2, 3, approximately in the middle of the box here. Okay, so I've tried my level best. You can plot a better diagram. However, remember to circle your points to make them visible. So I'm trying to fit this on the same page so that I can draw a balanced line of best fit. Okay, so those are my points. So I'm going to use a ruler to draw a line of best fit. If you try to be very perfect, these points are going to be on a very good line of best fit. Okay, I hope I've tried. You can draw a better line of best fit. At least you try to balance the points. Mine may not be balanced because my plotting may not be very precise, but of course you don't aim at joining the first and last. You just try to balance the points. You ensure that most of the points are just touching the line. If you plot them correctly, they should be just touching. 1, 2, 3. Okay. I think I can try to bring this line below. I need to do this. Let me try my second attempt. Okay, I think this is a better line of best fit because most of the points are just touching the line apart from one above. I can check if I plotted it correctly. The first one was 8.174. I will check it again. No, it was 83 against 6.174. 6.174 minus 6.0 divided by the scale 0.05. Those are three small boxes. Let me check how many did I add. 1, 2, 3. It's correct. It's correct. Okay, so that's going to be my graph. Next, I'm going to draw the error bars. I've also written the error bars on paper so that I don't keep going back. So remember to draw a nice error bars. You can always, of course, when I expand my line, it appears as if the points are very far, so you can try yours. So the error bars, you can use, you just pass the pencil through several times so that to make them bold and beautiful. I will try to make my pencil thicker or my pen thicker. Although I'm drawing this in blue, you are supposed to use a pencil for this. Okay. So the first error bar was 4.2. Of course, you should be knowing the scale. The scale on the vertical is 0.05, each small box. So 4.2, I'll just divide the 4.2 by the scale. 4.2. I hope I calculate the scale correct. 5 minus 4.5 divided by 10. Okay. So I have 4 point. What is this? Each small box is 0.05, and I want to draw. Oh, I was drawing on the wrong axis. They're supposed to be horizontal. And the scale on the horizontal is 30 minus, that is 10 divided by the scale on the horizontal is 1, so I want 4.2. So I'll count 4 boxes to the left and 4 boxes to the right. So 1, 2, 3, 4. I'll just approximate this to just 4 because it's 4.2. Then on the other side, 1, 2, 3, 4. Then I pass the pen. Of course, you are supposed to use a ruler here to pass your pencil. Pass your pencil twice so that they look very beautiful. The next one was 4 point. Next, what is the next one? I missed it. 3.1, 2.3, 1.5, 1.3. So the next is 3.1, then 2.3. So 3.1, I will count 3, a half, 1, 2, 3 is almost here. A half, 1, 2, 3 is almost here. Then I join these. Okay, the next is 2.3. So I'll just set a half, 1, then 2 is almost here. A half, 1, 2 is almost here. It is 2.3, so I just estimate this. The next one was 1.3, 1.5, then 1.3, then 1.2. 1.5, so that is 1.5. So 1.5 almost here. 1.5 is almost here. Then next is 1.3. I'll just take almost 1. Then 1.2. I'll just take approximately 1. Okay. So you can try to draw better error bars as long as you notice that they are horizontal. Then the next thing is to draw the line of worst fit or the worst acceptable line. So last time I taught you a simpler method. You can either try to check if you join to the top of the top error bar and the bottom of the bottom error bar and see if all error bars are crossed. If they are crossed, you can proceed with that line. If they are not, you change the technique. So I'm trying to join from the left hand side. Okay, it works. If I join from here, I see that all the error bars are going to be crossed. But I have to repeat this. Okay, so I try to join the right hand side of the top error bar to the left hand side of the bottom error bar, and also ensure that all the error bars are being crossed. If they're all crossed, then it means the line is good enough to go. So I have to label my lines. I'll call this one the worst acceptable line. So I join the right hand side of the top error bar to the right hand side of the bottom error bar here, and you are allowed to use a different color for the line of worst fit. You may not use a pencil. So this is going to be the worst fit line, and this is going to be the best fit line. The next thing is going to be finding the gradient. So I'm going to draw a triangle or triangles. If I can have 2 points for both lines, that would mean I would draw one triangle. If I fail to find those 2 points, I can draw 2 triangles for the gradient. But when I look at this, my lines may not be perfectly straight because I'm drawing on a computer. but I'm trying to look for a simpler point. Okay, I could even use these 2 points here. Then this side, it's like the lines are meeting, so I'll just choose 1 point. If you draw a better line, they may not be meeting. So I'm assuming that all my lines are passing this point. So I have to draw a triangle. Make sure your triangle is visible. Use a ruler. Ruler so that it looks nice. Okay, so the points here it is going to be the same point. So it is this is 27. So I have 27 on the x-axis against this is one small box. So I will subtract 2 minus 0.05, which is 1.95. It is the same for both lines. Then here I have up and below. Below I have this point. Let me change the color. So I have this point here and this point here. Above, on the x-axis, this is 20. That is 78 on the x-axis for both. So this is 78, 78 for both. On the y-axis, they change slightly. So this is 60. For the green one, it is going to be 65.6. I'll add one box on 5.5, 5.5 plus 0.05. That is 5.55. Okay, so it is 5.55. Then the top one, I'll add another box plus 0.05. So it is 5.6. The top one is 78 and 5.6. So I'm going to transfer these numbers so that I can find the gradient. So for best fit, of course, we're not supposed to write here, but I'm just writing here and then I'll transfer to the space provided. So for the best fit, the gradient we have the y values, we have 5.6 minus 27, no, minus 1.95. 1.95 divided by, on the x we have 78 minus 27. That is for the best fit. Then for the worst fit, we have 5.55 minus 1.95 divided by 78 minus 27. Okay, let me just transfer these ones to the space provided. So you will simply say gradient of the best fit, which will be 5.6 minus 1.95 divided by 78 minus 27. Is that true? Okay. Then the other one is 5.55. 5.55 minus 1.95 divided by 78 minus 27. So I'll just press my calculator. 5.6 minus 1.95. So this is 3.65. Oh, I've not divided. Divide by 78 minus 27. So it is 0.0716. Okay. 0.0716. Then for the worst fit, I have 5.55 minus 1.95 divided by 78 minus 27, 0.0706. 0.0706. Then I have to find the uncertainty, which is going to be the difference between the two. So I will say the steepest. Did I change these lines? Which one is steeper? Oh, I drew the worst, the shallowest. So it is going to be 0.7. So 0.0716 minus 0.0706. 0.0716 minus 0.0706, which is 1 times 10 to the power of minus 3, or it is 0.001. So I'll write my answer here as 0.0716 plus or minus 0.001. Or I can write 0.072 plus or minus 0.001. Okay, so that is my gradient. The hardest part is plotting the graph. Determine the average frequency of the power supply. The student measured the frequency of the AC power supply twice. Measured it twice. So we have 101 hertz and 97 hertz. We want the average. Of course, the average would be 101 plus 97 divided by 2, which I think this is 99. Then the uncertainty is going to be half of the range, absolute uncertainty and the frequency, because they have repeated twice. So we have half of the range, which is going to be half of 101 minus 97, which I think it is 4 divided by 2, which is 2. So F is going to be 99 plus or minus 2. Using your answers to A, C, Roman 3, and D, determine the value of C, include an appropriate uncertainty. So we saw earlier on that the gradient was 1 over 2 pi fc, I think. So it means, remember, the gradient from the first part of the question was equal to 1 over 2 pi fc, which means C would be equal to 1 divided by 2 pi f times the gradient, which is going to be 1 divided by 2 pi f is 99, because we are using the answer in D, 99. Then the gradient is 0.0716. Did I add the powers of 10? Sorry. I must add here in the denominator times 10 to the power of minus 3 times 10 to the power of minus 3. So this becomes times 10 to the power of 3 times 10 to the power of 3. This will still become times 10 to the power of 3. So this value, I must change it. So this becomes times 10 to the power of 3, 1, let me see, 0.0716 exponent 3. So this is going to be 71.6 plus or minus, this is going to be 1. Yeah, it is plus or minus 1. Okay, so this is 71.6. So this is going to be times 71.6. Okay, so I'll just press my calculator. 1 divided by open brackets 2 pi times 99 times 71.6. So that is 2.25 times 10 to the power of minus 5. So I'll write 2.25 times 10 to the power of minus 5. So the power of 10 is most likely going to be minus 5. So those are three significant figures. So the power, because the FC was capacitance, I can say farads. But if I use the gradient, F is, this will be 1 over, F is frequencies per second, and the gradient on the vertical it was a ratio which was tan theta, on the x-axis it was per ohm, so this is per second divided by per ohm, no, per second times 1 over, the gradient is, what is the units for the gradient? Let me check. So on the vertical we have no unit, on the x-axis we have per ohm. So it means the units for gradient has units as ohms. So this is going to be divided by ohms. So the other unit could be seconds per ohm. Because gradient alone has units as ohm, then 1 over per second for frequency, then times ohms for gradient becomes seconds per ohm. Then percentage uncertainty in C, I'll just use the expression above. So the percentage in C, because 1 over 2 pi is a constant, I will ignore it. Then for F, I will say absolute in F over F plus the gradient to be absolute in the gradient divided by the gradient. Then I'll multiply this by 100. So that is percentage. So for F, I think it was 2 divided by 99 plus for the gradient it was 1 divided by 71.6. Then I multiply this by 100. So you have 2 divided by 99 plus 1 divided by 71.6 times 100. So this is giving me 3.4%. 3.4%. So the percentage uncertainty 3.4%. This is the easiest method. Alternatively, you can find the maximum of C, which would be 1 over 2 pi times F maximum, then times gradient maximum. Then you subtract from the value of C that you obtain. So this is another method. So this would be 1 over 2 pi. The maximum value of F is 99 plus 2, which is times 101, times the maximum value of gradient is 71.6 plus 1, which would be 72.6. That would be the maximum. Then the answer you get, you subtract it from the value of C you obtained earlier on. So this would be 1 divided by 2 pi times 101 times 72.6. So this would be 2.17 times 10 to the power of minus 5. Yes, that is the maximum. But is it maximum? No, this is minimum. So if C is maximum, F must be minimum, not maximum, because it's in the denominator, it must be minimum. So I'll just change this to minimum. Instead of repeating myself, I'll just change this to minimum. So this is if this is going to be, if this is maximum and this is maximum, then C is minimum. So I'll just change this to C minimum. So this is minimum value of C. So I'll just now subtract the exact value of C above and the minimum value of C to get the absolute, or the percentage uncertainty in C is going to be the difference between the two, which will be 2.25 minus 2.17, 2.25 minus 2.17, of course, times 10 to the power of 5, divided by the true value, which is 2.25, then times 100, times 10 to the power of 5. 10 to the power of 5 cancels. 2.25 minus 2.17 divided by 2.25 times 100. So it is giving me a 3.6%, very close to each other. And the last part, the experiment is repeated using the same power supply and capacitor. Determine the resistance of R that would give a phase difference of 40 degrees, include the absolute uncertainty in your answer. So remember we said the gradient. What was the gradient first of all? The gradient is 1 over 2 pi f times c, but now we now know what 1 over 2 pi f c is, so the gradient is equal to that. So the gradient was equal to 1 over 2 pi f c. That was the gradient, and they are saying the gradient is 1 over 2 pi fc. So the experiment is repeated using the same power supply and capacitor. Determine the resistance of R that would give a phase difference of 40 degrees. Remember the original equation we started with, we said that tan of theta is equal to 1 over 2 pi f times c times R. And remember this was the gradient. So it means R is going to be equal to tan theta. No, this was in the denominator, so it means this is 1 of R. So it means R is going to be equal to the gradient divided by tan theta. So the gradient divided by tan theta, so our gradient was 71.6 divided by tan theta, which is tan of 40. Then our R is going to be 71.6 divided by tan of 40. So R is going to be 85.3. Then plus or minus the uncertainty. So I'm going to find the absolute in R. Since I have gradient divided by tan theta, and tan theta is a constant, I'll just ignore its uncertainty. I have the uncertainty for the gradient. So this will be absolute in the gradient divided by the value of the gradient, then times the value of R. So the absolute for the gradient was 1 divided by the gradient, which is 71.6, times the value of R, which is 85.3. So this is 1 divided by 71.6 times 85.3, which gives us plus or minus 1. So that is going to be the absolute uncertainty in R. Okay, so I have tried my level best. My answers may not be exactly accurate, but I've tried my level best to give you a clue of what is necessary here. By the way, I could also have found the absolute uncertainty in R by considering the absolute uncertainty in F and the absolute uncertainty in C, because from this equation here, when I make R the subject, R is going to be 1 over 2 pi fc times tan of theta. And since theta has no uncertainty, I'll just ignore it. So it means the absolute in R would be equal to the absolute in f over f plus the absolute in c over c. Then I multiply this by our value of r. This would also give us the same, approximately the same value. Okay, I've tried my level best, and I think you might have picked something from this video. Until next time, bye bye.